I'm Shelley Begley, and I'm going to be discussing fast and accurate and non-destructive solutions to materials test up to 1.1 terahertz. That works, yes. So it's a lot of information to go over in 15 minutes, but first we'll talk about, we're going to be measuring permittivity and permeability, and I'll explain that a little bit. And then we'll go through a very brief overview of a lot of methods, and then I'll show you a 1.1 terahertz system that we put together. Okay, so permittivity and permeability. These are represent the interaction of a material in an externally applied electromagnetic field. And we have, so permittivity is the dielectric properties, and it's represented by the Greek letter epsilon and the little r there. Let's see, I'm supposed to be doing this. The little tiny r there is because this measurement is relative to free space, so it's basically a ratio, and with that ratio we get rid of any units, so it's a unitless measurement. And it's complex. So we have the real part and the imaginary part. The real part represents the storage of the energy from the field in the material. And this is a kind of a reciprocal thing during the cycle. It gets stored and released and stored and released. And during that process, we have some loss. And that's represented by the imaginary part. Okay, and so the magnetic properties are designated by the Greek letter mu. And it's the same thing, where we have the real and imaginary part representing the storage and the loss in the material. And you'll also hear of tan delta, and this is just the ratio of the imaginary part divided by the real part, and it kind of gives you a relative, an idea of how lossy your material is relative to what the dielectric properties are. They're also often called dissipation factors. So you'll hear all these terms, but this is what they mean. Okay, so there's a lot of methods here, and it can often seem very confusing, like a big puzzle, and which to choose, you know, is, people ask me all the time, which is best? Which is best? What do I want to do? And they, of course, they'd like the one answer that fits all problems. And that's just not the case at this point in time. So we have a lot of variables it depends on, and this is a big long list which we don't have time to go through. So I'm going to simplify it here and shorten up this list to the top three. So we have frequency of interest, which pretty much determines which analyzer you're going to choose. You have a LCR impedance analyzer or a network analyzer. And then the form of the material, whether it's a liquid or a solid or a powder or something soft or hard, and then these expected values of epsilon and mu. And those will kind of determine which little fixture, sample holder, method that you choose. Okay, so we're going to graph all these things to sort of maybe give you a picture representation. So first we'll look at the LCR and impedance analyzer solutions, and we have frequency across the x-axis here, and then I divided it between, try this one. I'm doing better here. Liquids and solids, okay? So first, as a parallel plate capacitor method. And this is just a couple of metal plates, and you put your sample in between, and we measure capacitance, and from that we can calculate permittivity. For solid materials, these plates clamp down on your material, so there's no gap. But for liquids, we also have a solution for liquids. The plates are at a known distance apart, and you fill this thing up with a liquid. And these solutions, depending on which fixture you choose, go anywhere from the hertz to 1 gigahertz. If you need to measure magnetic probability, and they're just for dielectric materials. If you want to measure magnetic materials, we have a magnetic text fixture, which is just a coil, and your material has to be shaped into a round shape with a hole in the center called a toroid or a donut shape, and fit into this fixture, and this will go up to 1 gigahertz also. Okay, and then we have a coaxial probe. This is an open-ended coax structure. At the very tip is open, and the field fringes into the air or whatever sample you put into it, and we measure reflection coefficient with this. And it's usually used with a network analyzer, but we can also use it with an impedance analyzer and go down to 10 megahertz. And so now looking at the network analyzer solutions, we can see our dielectric probe kit, the coaxial probe method, and Agilent has these probes up to 50 gigahertz, and other companies make them higher frequency that will work with Agilent network analyzers. All right, so coaxial probe is best for liquids or solids or that are soft, or something conformable that can press right up to the probe tip and not leave an air gap, because that can cause significant error. Okay, moving on, we have a resonant cavity method, and this is mostly used for thin sheets of material that are very low loss, usually printed circuit board materials or some kind of ceramic packaging materials that have a very small imaginary part of permittivity. And it works a little different. We have a resonance in the fixture, and we measure the frequency and the quality factor of that resonance. We put a material in, and it shifts downward, and the quality factor degrades, and we can calculate the real and imaginary part of permittivity from that. There's lots of different types of fixtures. Here's just a few. We have a split cylinder resonator, a split post dielectric resonator from a company named QWED, and they're right over here. And we have one also at our booth. And then if you need to go, these go up to maybe 20 gigahertz. And if you need to go higher, you can get an open resonator, and these have a couple of mirrors, and your sample goes in between. And these are very sensitive measurements for thin materials or very low values of the imaginary part of permittivity. Okay. All right. So one of the real workhorses in these measurements is the transmission line method. And in this method, you cut your sample to fit inside a waveguide or a coaxial airline. And this method, on the low end, is sort of a practical consideration of maybe 500 megahertz or gigahertz, where your wavelength gets too long to get enough sample to be able to make a sensitive measurement. And at the high end, it gets limited by the practical ability to machine your sample to fit in some tiny waveguide structure. And so usually at high frequencies, we launch out into free space with some antennas. Now you get a couple of antennas pointing at each other, and a sample in the middle. And so I'm going to show you that system. So here we have a network analyzer. This one just happens to be a PNA-X with the dual source, and connected to it is Virginia diodes, frequency extenders from 750 gigahertz to 1.1 terahertz. And our sample is fixtured in the middle between the two antennas, and we're measuring S parameters. So we're measuring S21, S12, and S11, and S22. And then we have some software that will calculate the permittivity, and we can also get permeability out of this measurement. Okay, so here's the system, and I apologize, the picture's a little dark. We took this picture at European Microwave Conference last year. And we have, this is the back end of the frequency extender. This is the sample, and the other frequency extender is on the other side where you can't see, and they come back, cables bring it back to the network analyzer. On the display, we're showing time domain. Are y'all familiar with time domain? Yeah. the yellow trace is time domain S21, and the blue trace is time domain S11. And we can see two big responses, one here and one here. And at first that was very confusing to us. We didn't know why we would see two responses from the sample, until we figured out that the distance between those two, the two responses was the thickness of the sample that we had. So what we're looking at here is a reflection off the front surface of the sample as we transition between the air and the material that the sample is made out of. And then on the second one is the reflection from the back side of the sample as it transmits from the material back to air. And we can see this because we have such a huge, frequency span when we get up to the terahertz, 750 gigahertz to 1.1 terahertz. All right, this is a close-up of the sample in a little fixture that we made, and these are the antennas here. And you can see it's very close together because we needed to get it close to get the transmission through. And here's the result. So this is S parameters first. The top blue line is the transmission through the material. And the bottom ones are the scallopy lines are the reflections, S11 and S22. And you can see clearly this beat pattern that was set up from these two large reflections that we saw. And then here is the dielectric properties. So we took those S parameters and we cranked it through an algorithm in the software, and we get permittivity. This is looking at the real part, and we get 2.01, which is very close to the expected value for the sample. Okay. All righty, so for more information about any of these methods that I briefly touched on, we have a website. If you just type materials into the Agilent website, you'll get to this page, which has little links to the product information about all the different fixtures. And also, we have some literature. We have a brochure, which is kind of a condensed version, and then we have an application note that goes into more detail about really the technical aspects of the different measurement methods. Or you can come over and talk to us at the Agilent booth. We have a demo there with the resonant cavity and the coaxial probe system set up, and we'd be glad to talk to you about whatever your measurement needs are. So, in summary, we have lots of solutions, up to 1.1 terahertz now, and we can be happy to help you determine which is the best for your needs. So, any questions? Nope? Well then, thank you.